So, hi there. Good evening to everyone. First and foremost, thank you very much for attending this Introduction to ANSYS Topology Optimization webinar. My name is Anas. I'm from Cybernet Systems Malaysia. So, as you all know, today's webinar is going to be about topology optimization featuring ANSYS products. If you have any questions at any points of this webinar, feel free to drop them in the chat box and I will try to answer all of them at the end of this session. Please remind yourself to keep yourself muted during the course of this webinar as well. So the agenda for today will be as follows. First, a little bit of introduction to Cybernet systems, then followed by the introduction to ANSYS. And then I'll tell you a little bit about the concepts of topology optimization. And then going through the topology optimization products features featuring ANSYS. Those products names is ANSYS Mechanical and also Discovery Live. And then we take a look at a demonstration for both of these ANSYS product for topology optimization. And then finally, we wrap up with the Q&A session. So let's start with a little introduction to Cybernet systems. Established in 1985, Cybernet system has been providing CAE solutions and also IT solutions in product sales through product sales, contract analysis, consulting, and software development for over 30 years now. We have developed a partnership with more than 20 companies, mainly in the United States, including ANSYS, Synopsys, and Symantec. The sales subsidiary of Cybernet System consists of Cybernet China, Cybernet Taiwan, Cyfam, which is based in Korea, and of course, Cybernet Systems Malaysia. So here as you can see, Cybernet System has been working with numbers of group companies around the world for both sales and also development. Then we go a little bit of introduction about Cybernet Systems Malaysia. Cybernet Systems Malaysia's office is in KL Eco City Bangsa and has been around for more than 1 year now. Cybernet Systems Malaysia was established in November 2018 as a fourth subsidiary in Asia. Our business here mainly revolves around providing CAE solutions, IoT solutions, big data solutions, and also professional services. Our partners up until this point in time include ANSYS, Synopsys, and many others. So as you all may know right now, Cybernet Systems provide all sorts of solutions. And those solutions are CAE solutions, and visualization solutions, big data solutions, and then we also provide AI service or IoT solutions, IT solutions, and also engineering services. Okay, now we move to the introduction of ANSYS. Founded by John Swanson in 1970, ANSYS is a global public company based in Canonsburg, Pennsylvania. It develops and markets multi-physics engineering simulation software for product design, testing, and operation. Now, as you can see on the slide here, those multi-physics include almost every conceivable physics analysis you can think of, ranging from a simple structural analysis all the way to the system simulation. For 50 years now, ANSYS has been the class-leading multi-physics simulation software provider. Due to that fact, ANSYS now has been used worldwide with over 45,000 global customers. Now, ANSYS is also used in a wide range of industries, including automotive industries, electric and electronics, aerospace, and many more. So this is basically the summary of what I said just now. But I want to highlight a little bit about the ANSYS mission. ANSYS for pervasive simulation. Now, what does it mean by pervasive simulation? Pervasive simulation is basically an integration across all physics on a single open platform. It means to use ANSYS as a versatile tool to be used throughout the design, analysis, production, and maintenance process. So right now, as you can see here on the slide, are the products of ANSYS. As I said it before, ANSYS provide multiple physics simulation for every type of need. That solution include mechanical solutions, fluid solutions, electronic solutions, design solutions, and also some additional options. Mechanical solution basically include analysis such as structural analysis, dynamic analysis, impact analysis, thermal analysis, fatigue analysis, and for today's webinar, topology optimization as well. And then also have a fluid solutions, which includes something like general purpose thermal fluids analysis, detecting mechanical fluid analysis, and so on. And then, of course, electronic solution include analysis such as signal integrity, power integrity, electromagnetic interference analysis, so on and so forth. And then ANSYS also provide a design solution, which mainly fit for designers. And then, of course, some additional options, which include a parallel computing module, material data selections, and so on. So let's get to know a little bit about the concept of topology optimization before we dive deeper and where it came from, basically. So the concept of topology optimization. Now, let's learn about the concept of topology optimization by taking a look at what is computational design is. Essentially, computational design can be referring to the use of computers and mathematical approach to the generation of geometries, objects, and architecture. It basically means that the computers are responsible for the design process itself based on the instruction given by human. This computational design has been showing a lot of excitement these days due to several factors. Firstly, the high-speed optimization nowadays is made possible thanks to the evolution of computers itself. Computers these days can handle millions and millions of calculations without even breaking a sweat. Another main factor is the rise of utilization of 3D printing in manufacturing. Now, as we all may know, the charm or the benefits of 3D printing is that some shape that cannot be manufactured by conventional manufacturing techniques can be made possible using a 3D printing process. And then, of course, finally, labor shortage has always been one of the motivations behind the emergence of most technologies we see today. The same case is applied to the computational design as well. So in the case of mechanical design, it's the structure and the shape of the design that was optimized to maximize the product performance. In other words, the objective function will lead to the optimized shape in stiffness maximization, natural frequency maximization, and also thermal diffusion maximization. Now, this structural optimization can be done using finite element analysis or FEA, such as ANSYS. As for the type of structural optimization, there are three different types of structural optimization. Those are the sizing optimization, shape optimization, and also topology optimization. Sizing optimization is when the dimensions of the design values as parameters. Then shape optimization basically optimize only the shape, meaning the outline of the shape is optimized. And then finally, the topology optimization. Now, topology optimization is the most flexible optimization technique. Now, by definition, topology optimization is a mathematical method that optimizes material layout within a given design space for a given set of loads, boundary conditions, and constraints with the goal of maximizing performance of the system. Like I mentioned before, we can maximize performance such as the structural integrity of the design, the thermal capabilities of the design, so on and so forth. Topology optimization differs from shape optimization and sizing optimization in the sense that the design can achieve any shape within the design space rather than working with predefined configuration. The one thing that needs to be considered when it comes to topology optimization is the feasibility or usability of the optimized shape. Because some of the optimization outcome may be difficult to be manufactured conventionally. But like I mentioned before, the growing of the 3D printing technology does help in dealing with these kind of difficulties. Okay, now, so let's try to position topological optimization in the development cycle of a product. So in the traditional development of a part of or an assembly, first model is tested using simulation, particularly instruction mechanics. After various analyses, the part is modified, and then we start again to meet the requirement of specifications. Now you see this efficiency of this process is highly dependent to the performance of the designers and also the smoothness of the exchange between the design team and also the simulation teams. So most of the time, one can quickly find oneself in a long process of trial and error until an optimal solution is obtained. So we need a tool that makes the connection between design and physics analysis. So here is where the topology optimization came into play. Like I mentioned before, topology optimization is attracting attention everywhere, basically. Now every CAD or CAE vendors, including ANSYS, has released its own topology optimization products or features, one after another. So when it comes to choose which products offer the best topology optimization, it all comes down to what it is that you needed the most. Is it the analysis speed and ease of use, or maybe scalability of the products, or even a functionality of the product itself? ANSYS offers several different types of topology optimization capabilities, ranging from the entry level to the very high end. Now, one of the ANSYS products offer the ease of use, intuitive, high-speed approach on dealing with topology optimization. The other products delivers a high accuracy optimization with much higher flexibility in terms of setting objective and constraint. So basically, depending on what you want or depending on your needs, ANSYS can offer product to fit most of your needs. So basically, everything is all up to the users themselves. What do they really want to achieve when using topology optimization, and what kind of process they want to go through to get to the optimal design that they want. Okay, now so let's see some of the features of ANSYS topology optimization products. Here we will dive into both ANSYS Mechanical and ANSYS Discovery Live. A little bit of overview for both of those products. And then we take a look at a typical workflow of topology optimization when using ANSYS. And also some couple of case studies to basically show you more the capabilities of ANSYS. So a little bit of overview for ANSYS Mechanical. So basically, there's three types of licenses of ANSYS Mechanical. In simple terms, basically, the license of the solutions are depending on the complexity of certain needs for analysis and simulation. The top of the range license provides the most access to different types of analysis and simulation, while the entry-level license gives you enough access to the general purpose analysis. Excuse me. So the first one is ANSYS Mechanical Pro. This is the least expensive license you can buy for ANSYS Mechanical. Compatible with general purpose content analysis, some transient thermal analysis, full thermal analysis, in fact, fatigue analysis, and also topology optimization. So you can get the topology optimization features of ANSYS setting from the lowest tiers of the ANSYS Mechanical license. Then, of course, as you go up, you get more and more features. You can you get access to more and more capabilities from the ANSYS Mechanical. Until you go all the way to the ANSYS Mechanical Enterprise, where for the topology optimization, you get 2 more additional features, which is lattice optimization and also additive constraints. So basically, if that's what you want for your analysis, you can go all the way up to the ANSYS Mechanical Enterprise license. If you want to know more details about which features includes which license, you can always visit the ANSYS websites. Okay, so we need, before we go more detail into the topology optimization, we got to talk about the ANSYS Mechanical Workbench. Now, this is the essential part of the ease of use when using the ANSYS. ANSYS Workbench is where you can manage all of your analysis or simulation process within one place. It is called a project schematic. It gives us the advantages to easily build your analysis workflow. So you can simply just drag whichever physics simulation you want from the left side of the window called Analysis System and drop it into this white region right here. It's called Project Schematic. The workbench also gave us the advantage to understand the analysis process more easily, because when everything is laid out according to the workflow, you can see and you can understand what is going on our analysis. Okay, now we've done with a little bit of overview of ANSYS Mechanical. We go to ANSYS Discovery Live. Now, what is ANSYS Discovery Live, you might ask? Now, Discovery Live is a software that is capable of basically fusing design and analysis into one. It is the first simulation-driven design tool to combine instant physics simulation and also interactive geometry modeling in a single user experience. Now, in the case of topology optimization, this ease of use and interactive experience make it even better for the users themselves. Main advantage of the ANSYS Discovery Live include quickly prepare model for simulation or create design variation for study. Then you can rapidly explore multiple design concepts with real-time interactive simulation. You can also refine insights with high fidelity simulation and also a different type of additional conditions. So basically, ANSYS Discovery Live will help either designers or analysts to get what they want in a way that no other type of software can deliver. It gives you an overwhelming speed in terms of simulation. The operation is simple. It is also flexible to keep a field of analysis in mind because the way it was laid out. And then, of course, you have the robustness of taking a look at the concept of the past and then bring it into the present as well. Okay, so this is basically what I said before. There are 2 types of ANSYS product that can that feature topology optimization. Those products are ANSYS Mechanical and also ANSYS Discovery Live. 2 of these products deliver a different type of experience and different types of way to get to your optimal design. I like to categorize this product based on who are going to use it and at which stage of design development cycle that this product will be used the most. Essentially, for ANSYS Discovery Live offer a very easy and intuitive approach to topology optimization with a high-speed solution capability. So therefore, I believe that this product is suitable for designers who do not too familiar with the world of the CAE, and also can be utilized the most during a conceptual design process. At the other end of the spectrum, we have ANSYS Mechanical that offer very flexible and also accurate topology optimization capabilities. It means that user can be really specific in setting up the design goal and constraints to get the desired result. For this one, most of the users will probably already familiar with the CAE. And then, of course, ANSYS Mechanical is useful to validate the final design of your product before you go and making an actual prototype. So this is these two products deliver the same thing, but with very different type of approach. So depending on what you want, you can choose between the Discovery Live and also ANSYS Mechanical. So here we have a detailed list of features for each product that I mentioned before. As you can see, for the optimized shape output, both Discovery Live and Mechanical are capable of producing smooth geometry and STL file output. Smoothing basically means a cleanup process of the generated STL file of the optimized shape. The rest of the features, however, ANSYS Mechanical is clearly more feature-rich, like I mentioned before. So having the features such as lattice optimization, extrusion constraint, and so on, users can virtually get the desired shape easily, as long as the input is correct. But as for ANSYS Discovery Live, although it is not as feature-rich as the ANSYS Mechanical, the speed of the solution and also the intuitiveness of it make it, desirable for the different group or different type of users, like I mentioned before. Okay, next we have the topology optimization workflow that you can expect when you're using ANSYS Mechanical. Here we have a typical workflow for topology optimization. For this particular example, the optimization, this optimization will be for a cylinder mounting shape of a rocket engine nozzle. By the way, this example featuring ANSYS Mechanical. So as you can see, for the first step here, we define our design space using CAD software, which in this case we are using ANSYS SpaceClaim to define our design space. And then next, we carry out a static structural analysis first as a reference for the stress and deformation for our model. Then afterward, we can start to run the topology optimization. So this is basically how the optimized shape can be obtained. After the optimized shape has been generated, the calculated topology optimization shape is usually basically uneven and composed of large number of facets. So the next step will probably be to edit or clean our optimized shape a little bit. Now, I believe there are several CAD software out there that can manage to do that. Basically take a faceted body and turn it into a usable CAD solid body. In this case here, we are using ANSYS SpaceClaim. Now, ANSYS SpaceClaim has the technology to smoothen out the rugged and uneven surface of the optimized design, and also capable of converting the faceted body into a workable solid body. Then finally, we will verify the optimized design with a structural analysis again by using the solid data prepared in the previous step. So here, the final step, we can check if the new and improved design actually satisfy our design criteria or not. and then changes can be made manually if needed. Okay, so before we go into the demonstrations, let's take a look at the ANSYS topology optimization capabilities. A couple of case study. So here, in this case, we have a simultaneous thermal and structural optimization of a heatsink. This will be using the ANSYS mechanical. In this case, as you can see, we are not only concerned about the thermal performance of the heatsink, but also the structural performance of the heatsink as well. For this particular case, we set the mass reduction to 20% as the response constraints. As you can see, the first optimization was done with only heat transfer as our design objective. Since only the transmission of heat is taken into account, the optimization shape is easy to understand, and a straight shape pipe was generated basically from the heat source to the fin. Now, for the second optimization, here we have only concern on the structural performance of our model. The heat source point from the previous analysis was fixed this time during the structural only optimization, and the pressure is loaded on the fin. So when you take into account both thermal and structural performances, the resulting shape will look like this. So basically, this shape is optimal for both having a good structural integrity while having a good heat transfer capability as well. Okay, now let's take a look at a lattice optimization of a seat frame. In this case, we want to generate an optimal design for the seat frame using a lattice optimization. This will include lattice structure inside our frame. First of all, as you can see right here, the circle in red is our design space where the optimization will take place. First, we implement the topology optimization to find the optimization shape. Then we get shape that looks like this first. The mass reduction of 40% with the several manufacturing constraints were included in our design constraint. So after the topology optimization was done, lattice optimization was performed for further weight reduction. So there are a variety of lattice type available in ANSYS. In this particular case, we use this one with a density range of 0.2 to 0.7. And then finally, the resulting shape is as follows, as you can see right here. If you look closely, we got a lattice structure inside our already optimized shape. So now let's go to the demonstration of topology optimization. The first demonstration will be about the helicopter pitch arm. This one will feature the ANSYS mechanical. We will be using ANSYS mechanical to do topology optimization for this one. So basically, the objective is to create a design alternative for our helicopter pitch arm right here. We have a typical criteria. We want to reduce the mass from the original design, and also we want to create a helicopter pitch arm that when stress imposed on it does not exceed 200 megapascal. And for this case, we are going to use structural steel as our material. For the second demonstration, we are going to do a topology optimization for a PC monitor stand. This one, we will be using the ANSYS Discovery Live as our topology optimization product. Objectives, again, we want to create a design alternative for this PC monitor stand. We have the same type of criteria. We want to have a less mass than the original design. We want also to maintain the structural integrity below its yield strength. And the material that we will be using for this one will be aluminum. So let's start with our first demonstration, which is going to be this one, helicopter pitch topology optimization. So here, as you can see, I've already done the topology optimization for this particular example. First, I want to show you this one, the original model, before we do any type of topology optimization on it. Okay, so as you can see, the original design does include this type of ridges inside the helicopter pitch arm. And then we apply a boundary condition such. As such, we have a force in that direction and also another force subjected to these two holes right here in that direction, and also a fixed support. In this case, you can see the stress imposed on our helicopter pitch arm is exceeding 200 megapascal. Now we are trying to find an alternative design that can have that can reduce this stress imposed on our helicopter pitch arm to be below 200 megapascal. So I'm going to show you sort of step-by-step procedures on how you actually make a topology optimization on the ANSYS, ANSYS Mechanical. By the way, this is what we call ANSYS Workbench. We have a project schematic here, and also we have an analysis system right here. So what I am going to do first is drag a static structural analysis here from our analysis system and drop it everywhere in our project schematic here, as such. And then also I am going to drag a topology optimization and drop it inside the static structural cell because we want to couple these two analyses together. So basically right now, as you can see, there's a linkage between these two types of analysis. Therefore, it will be related between these two. And of course, I'm going to drag this geometry. I'm going to use the same geometry as the one I've done before. So if we take a look at the engineering data, we already have defined our material, which is structural analysis. And then let's go into this first. If you already have any questions in your mind, you can start to write it down on the chat box, and I will answer your questions at the end of the session. Okay, so now here we have our helicopter pitch arms loaded into the ANSYS Mechanical. As you can see, we modified this area right here. We create a new design space to find to be used for the topology optimization. And then we have 3 different parts. And then what I'm going to do first is actually create a new coordinate system. Here. as such. And then we take a look at the connection between our parts. We have these two bonded together like we intended to. And then I'm just going to quickly mesh our model right here. As you can see, this model is already meshed. If you want to add a little bit more detail on our mesh, say for example, we want to increase our mesh right here on our design space, you can easily do that by right click here on the mesh, then insert sizing. For the geometry, you select this part right here, apply. And then I believe for the size, we can try with 2.5 millimeter. And then we can regenerate the mesh again. As you can see, this particular mesh right here on our arms has been increased. And then of course, the next step will be defining our boundary conditions. So what I'm going to do is select this part right here and then apply a fixed support. So basically this particular surface right here will be fixed in place. This surface right here will not be moving translationally or rotationally. And then we are going to increase some loads. First, I want to put a load right here. For this case, I want to use something that we call as remote force. Right here, remote force. And then I'm going to use a new coordinate system. For the magnitude of our force, I will be applying 1000 newtons of force in this direction, and also a little bit of force in that direction as well. So according to our new coordinate system, I'm going to put 1000 here, and then 100 newton here. And then for the location, I'm going to change it. Okay. 1000. So we have our force applied to this particular part right here. And then I'm going to put the force in this surface right here. Yeah, basically the same thing. I'm going to put a force around 1000 Newton to this negative y direction, and also a little bit on the negative z direction as well. There, and also there, something like that. And as for solution, I'm going to be interested in the total deformation and also the stress of our part. Whereas for the structural analysis, I'm going to just try and solve it right here. Depending on the size of your meshing or what kind of hardware are you running, the simulation will depends on that. Okay, it's basically done. So here we have the information of our I got the pitch arm right here. And of course, the equivalent stress, as you can see, it's still from this the maximum stress imposed is still around 200 megapascal, which is something that we want to try to improve without topology optimization. So now we've done with our initial step, which is the structural analysis. We go into the topology optimization. Now, as you can see, we have a numbers of constraints that you can choose from for the topology optimization in the ANSYS mechanical. Later on, I will show you the topology optimization of the discovery line. And you see there's quite a large gap between the constraint or function that you can use. To take a look at the analysis setting of the topology optimization, this is basically how you control your calculation or your analysis. For the optimization region, you can select which region you want to choose from for the topology optimization. Exclusion region, you can choose between boundary condition or geometry selection or even name selection, depending on how you define your model. So by default, all of the boundary condition will be excluded from the optimization. So therefore, if you remember this particular part right here, it will not be optimized. Therefore, this surface will stay there. But in our case, we only want to optimize this arm right here. Therefore, for this one, I'm going to exclude this region and this region. So basically, we have this design region for our topology, and then these two right here will be excluded from the optimization process. And then, of course, optimization option right here, as you can see, you have different type of like ways you can do your optimization from. Here, like I mentioned before, we have lattice optimization as well. If that's what you want, you can choose here on the optimization option. We have density based, which is a very typical type of optimization. And then, of course, level set based, which is almost similar to the density based, is a different type of approach. And then also we have a morphing topology optimization. For this case, I'm going to use the density based topology optimization. So now the objective here, response type, you can change. There will be a compliance, or we want it to be a mass, volume, or even an entire criterion you want. And then as for goal, you can minimize or maximize depending on the response type that you choose from here. And then this formulation, either force or displacement, depending on your needs or depending on how you set up the topology optimization. Environment name, in this case, we are considering about the static structural. So therefore, this is the only thing that is have right here. Then, of course, you can set your start step and also end step for your objective. Then, in this case, this response constraint is already loaded by default. So here in the response, like I mentioned before, you can choose between different type of response that you want, depending on what type of outcome that you are trying to get. Here, as you can see, you have mass, which is one I'll be using right now. You can also set your response to volume, and then you can change even to center of gravity, global or local von Mises stress as well. So if you want this to be your response, you can select here on the response definition. And of course, displacement, reaction force, so on and so forth. In this case, I'm just going to stick with the mass with a volume mass reduction to 50%. So we retain 50% and we reduce 50%. And then if you can see here, is what I mentioned before. And then you can also set a manufacturing constraint, because some of the manufacturing process does limit on how you can design your model. So the manufacturing constraint does help in make a more feasible or manufacturing friendly outcome. Here you can see you can set a member size, which basically almost set a thickness for your final optimized shape. And then pull out direction. This one is very good or very convenient for a casting process. And then we also have the extrusion, cyclic, if you want to create an optimized shape, something that is have a cyclic symmetry. And we also have a normal plane symmetry for manufacturing constraint as well. So you can simply just run this analysis by right-clicking here or even click solve here, but it can take quite some time to finish. So therefore, we are just going to take a look into the final product. So if you see right here, this is our optimized shape of our helicopter arms. And then after you've done that, you can simply right click here. You can either export it as STL file or even as a smooth STL file to be used later on to do a what we call a validation process to our newly designed model. So here, after you've done cleaning this particular model right here, you have something that looks like this. So this is basically the optimized shape that has been generated by the ANSYS mechanical based on your input on the topology optimization menu. So you can see we have a similar type of force, remote force, and also fixed support. And then you can see the stress here has gone slightly under 200 megapascal, which is our initial design criteria. And therefore, this shape has achieved that criteria that we've just set. And of course, we can also see a total deformation of our newly made shape right here. So this is a validation process of our new model. So basically, that's how the topology optimization process looks like in the ANSYS mechanical. You have a geometry, and then you use a static structural analysis to do an initial analysis to see the structural strengths, so on and so forth. And then you can couple it with the topology optimization. Here is where you can set all types of all types of constraint or response type, or what kind of outcome that you want to see. You can set all of that here in topology optimization. And then finally, using the result from this topology optimization, you clean that faceted body into a solid body, and then use that into a validation system. So that's how topology optimization works in the ANSYS mechanical. So for the next part, I'm just going to go quickly and go with the ANSYS discovery life for our second topology optimization right here. Again, if you have a question, you can start to ask the question right now in the chat box, and I will answer the questions then after the demonstration. This may take quite some time. Okay. So here, as you can see on the screen right now, is what we call the ANSYS Discovery Live. Here we have already, as you can see, a different type of GUI. I believe this is more appealing to the user's eye. So first, what I'm going to do is import our chat file. So how I'm going to do that? Sorry, let's go with file and open, and then I'm going to locate my chat file and search. So now, as you can see, we have our monitor and also the stands. In this case, the topology optimization will be done only on this body right here and then this body right here. So therefore, all of this will be suppressed and not included in our topology optimization. Okay, so how we are going to start our topology optimization with the ANSYS Discovery Live. We go to this part right here, create solution, and then going to start with structural study, and then select aluminium as the material for our stands. And then we need to select the bodies of our analysis. So I'm going to select this body and this body right here. Then click yes. Now we are already into our analysis environment, structural analysis environment. What I'm going to do next is define a boundary condition. Under here, I'm going to define a fixed support. And then I'm going to hide this and select this region right here and give it a force. Now the force is going to be facing in the, I believe, negative Z direction. So fairly typical monitor size, monitor weight. So say negative 60 Newton right there. Then we define our boundary condition already. So we can simply just click play here and start simulation. As you can see, it's already starting simulation, and then we already have the result of our simulation just like that. So there's a Discovery Live can give you the result of your analysis really, really quickly. You can see here on the left side, on the right side, I'm sorry, we have our deformation of our stand right here. And then if you go to different type of different menu, you can go with, you can also see the volume stress as well. As you can see, we have 1 megapascal of stress right here on this particular region. Okay, so now we've done with the static stress analysis very quickly because that's what ANSYS Discovery Live do. Next, what we are going to do is we are going to add a topology optimization like that. Here we have the topology optimization volume graph. I will update as the simulation goes along. And then I will also add 2 more graphs, which is one is the max stress in the volume, and the other one is the max deformation of the volume. So now we have 2, and then we will monitor this graph as the topology optimization take place. Now the topology optimization already enabled. For the target, in this case, we only have this body, so we only have this one analysis, so it will going to be a structural analysis. Now, as for the goal, in this case, for discovery life, you can only choose between two, which is to minimize the volume or maximize the stiffness. In this case, I'm going to choose maximize the stiffness of the stand right here. Then again, same as before, volume reduction to control. In this case, I'm going to select 50%, I guess. And then, of course, constraint here. To select here, you can select between different type of constraint that you want to use. Like I said before, Discovery Life is not as feature rich as the ANSYS Mechanical. You can only have this constraint right here, pull through, so on and so forth. So, okay, I'm just going to stick with it. So to start our topology optimization, first I'm going to do this a little bit, I guess, here. And then how to start, we are just going to click this before. Then as you can see, right here, topology optimization, the optimization is currently already underway, and then you can monitor it. The volume, the max deformation in volume, and also the max stress in volume. So basically everything happened in real time. You can monitor everything in real time. That is one of the main advantage of Discovery Live. Now you can see we already have a design point 2, which have a slightly lower volume and obviously increase max deformation and also max stress. Now you can see as the optimization take place, like in the ANSYS mechanical, at the boundary condition, there's no topology optimization on the boundary condition. So the boundary condition surface will be excluded from the optimization. As you can see, the base right here, where we fix the surface, is not affected by the optimization. And then also this gap right here and the size of this right here will also not be affected by the optimization. Yeah. So you can either let it finish until it reach its design goal, or simply if, say, for example, monitor this maximum stress and maximum deformation here, and then you already found that sweet spot or that design that you want. Say, for example, I'm already satisfied with this maximum deformation and maximum stress. I can just simply click pause right here. And I can start to convert this into a facet poly. Now, as you can see the difference between the optimized shape and the original shape by this line right here. Now I'm going to convert this into a facet. As you can see here, I can convert this result into facet. Then we have a converted result right here. I'm going to move it to the side. Then I'm also going to convert into a smooth facet. Because it will be easier for the user to use it later on, to do validation or so on and so forth. Plus, with the discovery life, you don't need to actually make this newly optimized model into a solid and then use and then make a validation in the discovery life itself, because as the topology optimization took place, this stress and the deformation are already updated, and therefore there's no need to do any validation in the discovery life. So here we can see the difference between smooth facet and also just a facet right here. Now this can be used later on if, say for example, you want to print it or something like that, or you want to do a simulation in the other software or something, you can use this faceted body as so now you can see the difference between the original design and also the optimized design right here. Very interactive way to do topology optimization in Unit. So that's basically it for the topology optimization of the ANSYS discovery. I believe we have covered both ANSYS mechanical and also ANSYS discovery. Same objective, but a very different approach for both of the products.